Okay, hi guys again. So last time we introduced formally the notion of a reduction. We discussed how reductions are a tool to relate different computational problems. And we saw an example of how a problem like linear programming, which a priori seems like some unassuming or boring optimization problem, in fact captures within it sort of general efficient computation in a very precise sense. Namely, every problem that is efficiently solvable can be reduced to linear programming. And so we proved that by arguing informally that the problem of circuit evaluation is in some sense complete among all efficient problems. That when we argue it somewhat informally, and then we separately formally argued that there is a reduction from circuit evaluation to linear programming. Now, maybe to some of you, this exercise may have maybe looked to some extent pointless because we can solve linear programming, we can solve a circuit evaluation. Why should we care about how problems are related? All we really care about is that we have efficient algorithms for them. So kind of all that matters is that we have good techniques to solve problems as fast as we want. That's maybe a reasonable point, but now we're going to apply the same apparatus of reductions in a world where we don't have the privilege of just saying, well, I don't care about reductions, I care about the fastest algorithm. Specifically, we can use reductions as a tool to understand the relations between seemingly intractable problems, right? So for problems for which we do not have an algorithm, we still want to make some progress and understand why we don't have an algorithm or how we don't have an algorithm. And pretty much the major and to a first approximation only tool that we have is to relate different intractable problems that helps us explain why certain collection of problems may look intractable. So today the plan is that we're going to start discussing intractability through the lens of reductions. So what I will do today is sort of pick up where we left last time by first introducing a general way to talk about computational problems, and that is through the language of relations and languages. Okay, and this is the formal way that computational complexity talks about general problems, and we'll see how we can use relations to express computational problems, and how to define the classes of P and NP using relations, and then we'll start talking about the theory of NP completeness. So today we start talking about interactability. And the first definition I want to put down is that of a binary relation. Okay, so a binary, so usually we don't really say binary, a binary relation is a subset R of pairs of strings. Okay. So an instance, an element in this set, usually it's called x, w, where x is the instance and w is the witness. Okay, so that's just a set, could be an infinite set. Now, whenever you give me a relation, the relation defines two natural computational problems. Okay, one is we're going to call it decide R. Okay, and it is the following problem. It says, given an instance X, okay, an instance is just a finite bit string. Decide if there exists a witness W. This is another string. such that xw is in the relation. Okay? So the computational problem, the side R, is the input that you receive is x. Okay? And what you're asked to do is to output yes or no, depending upon whether it is or not the case that there is a w such that the particular instance x that was received as input, comma w, is in the relation R. There is another problem that is another computational problem associated to R. We're going to call it search R. Okay? Which says, given an instance x, find a witness w such that x of w is in R if one exists. It could be that there is no such w. Okay, so kind of here the output is a yes-no answer. That's why we call this the side. And here the output is kind of the solution to the problem, or like the witness. So it's not a binary, not necessarily a binary output, it's something. Now clearly, if you are able to solve search R, then you're also able to decide R, because if you did find a valid witness, then it is because there is one. If you didn't, then it's because there isn't one. Less clearly is if you can solve decide R, are you able to solve search R? I think at some point there might be like some homework problem that sort of you will see that there's actually a reduction the other way. Okay, but so this is one way to express abstractly a computational problem, and I want to maybe sort of illustrate this with an example, kind of what this could be. So we've been using the example of max flow. So let's use it further to kind of illustrate how max flow can be modeled as a particular kind of relation here. Okay, so instances x are tuples that look like GST, right? Where G is a network, S is a source, and T is a sink. Okay? So witnesses W are a kind of ST flows. Okay? And a particular x comma w, which again is a GST comma F, is in the relation max flow if and only if F is a maximum ST flow in the network G. So this is how you can model the max flow problem using relations. Now the decision problem for this relation, R sub max flow, is kind of degenerate, right? Because it's asking, is there a maximum flow on the network? Well, there always is one. Okay, so kind of the answer to the side is always yes. So it's kind of a bit of a degenerate problem. Now the search problem associated to this binary relation, though it is interesting because it is saying, look, given an instance, in this case it is the graph, the network, together with the source S and the sink T, it is asking, please find a witness, in this case an ST flow, such that it is maximum on the network. So we have the search problem associated to this binary relation exactly models the search problem. Okay, and indeed, for example, in in certain instances, the Ford-Fulkerson algorithm exactly solves the search problem associated to this relation. Okay, so this should give you a sense of how relations behave. Again, you can typically think about the instance as the kind of the input to your algorithm, right? Because it's given an instance, given an instance. And in the decision problem, you're not necessarily asked to output a valid witness. You just need to decide if one exists. Because certainly finding one is enough, but you don't have to if you all have to do is decide. Okay, so that are binary relations. And binary relations are going to be kind of the abstract way that we think about computational problems. Now, another definition that I should put here is that you will find when you learn about computational complexity is the notion of languages, okay? So a language denoted usually L is a subset of 0, 1 star, okay? So it's just some possibly infinite set of finite bit strings. I mean, finite size bit strings. And anytime you have a relation, the relation defines a corresponding language. So the language L corresponding to R is, so L, where X is such that XW is in R, okay? So the language corresponding to relation basically corresponds to all the so-called yes instances. So all the X's for which there is AW, okay? All right, so these are like languages and relations are really the bread and butter of talking about sort of, or at least the basic sort of notions that let you express computational problems, at least for the classes P and NP that we're going to talk about today. So because we want to discuss computational problems in a very abstract sense, a first question that maybe is natural to ask is that, is it the case that for every relation R, the side R, or rather, let me write it like this. Is it the case that for every relation R, the side R can be solved efficiently? Right? So now that we have a way to discuss computational problems abstractly, we can ask, okay, so there is a computational problem which is given X, decide whether there is a witness for X in the relation. We could ask, is it always the case that we can find an efficient algorithm for it? So in the case of MaxFlow, it's a bit degenerate, but this is basically asking, are there hard problems, okay? But we know the answer, to some extent, is no, right? We can define some very difficult relations to decide. Perhaps the quintessential one that you might have seen in other courses is the halting problem, right? We can model the halting problem as a relation. So consider R of X W to be a kind of 1 if and only if let's say halt of X is W. Namely, what is halt of X? It says take X, think of it as an algorithm, decide whether the algorithm halts, and where now W is, let's say, a bit. Let me say beep for the witness is B, and the witness says, actually, I want to change this slightly. I'm gonna make the witness that doesn't matter, so I'll just put a bottom there. So even without witnesses, you're gonna say that X is in the relation, okay, regardless of witness, if and only if it represents a program that halts, okay? And we know through the undecidability of the halting problem that there is not just no efficient algorithm that decides this relation, there's just no algorithm, period, regardless of its running time, right? So by the undecidability of halting problem, there exists no algorithm A such that A of x equals a R of x comma bottom, comma bottom. This is even regardless of A's running time. Okay? So this is telling us that maybe we don't really want to consider all binary relations. We want to restrict our attention to binary relations that are at least reasonable, okay? We want to study binary relations where they're kind of well behaved. We want to kind of rule out the fact that maybe the binary relation encodes something so difficult like a halting problem. So so because of this, we're going to focus on binary relations that are efficiently computable. Namely, there exists a so-called a verifier algorithm. Usually it is denoted as V. I'm going to use V sub r because it corresponds to a particular relation, such that V sub r kind of implements the decision of the relation. Okay? So it is able to tell me, like, the relation so far was just a set. It wasn't an algorithm. Okay? That's why we could define something like the halting problem. But now we're saying that, no, look, the relation comes together with an algorithm that says the right thing. And this algorithm, the running time of this algorithm is in polynomial time in the instance. Okay? So this is another way to say it, is that when we can see, if you give me a candidate witness, I can tell you whether the witness is a good one or not for the current instance. All right, so now this gives us some structure to work with so that we kind of have focused ourselves to computational problems that are, let's say, reasonable, okay? And we can immediately make some observation, right? So we want to understand for a general R, how hard is it? So let's ask me the question now, which is, how hard is it to solve the side R now? So with this assumption, okay? Is it the case, for example, that we can always decide R efficiently? Well, the first one observation we can immediately say is that this restriction says that there is always an algorithm that may be slow but will decide R, unlike, for example, in this case where there's just no algorithm, right? So say observation. If R is efficiently computable, then the side R can be solved in a 2 to the poly x time. Okay? So namely, if R is well behaved, it doesn't encode some funny problems, then the decision problem associated to the relation R is not that hard. We can at least solve it in exponential time. Okay, this at least puts some, it's kind of some calibration. That's something, right? So let's look at the proof. Its proof is pretty simple. Kind of consider the following exponential time algorithm. So let's call it A sub R of X. So we want to solve the decision problem associated to R. So we're receiving X as input, and we need to decide, is there a witness? Okay. So the way it's going to work, it's going to say, well, we're going to try every possible witness, and because of this assumption that R runs in polynomial time, that V sub R runs in polynomial time, the witness associated to X cannot be more than polynomially larger than X. So it suffices for us to consider all possible polynomially sized candidate witnesses, and then we check for each one of them whether it happens to be a good witness. If so, we just output yes, okay? Otherwise, if we went through and tried all of the witnesses and for none of them we output yes, we're just going to output no, meaning that we have established that no valid witness exists. Now, the running time of this algorithm is 2 to the poly x times the time of running the verifier, but this entire thing is 2 to the poly x times poly x. So that is 2 to the poly x. All right. Now, the algorithm that we just wrote down is something that is known as brute force search. That basically says, because R is sufficiently computable, the decision problem associated with it has a well-defined search space. All witnesses of polynomial length, like all binary strings of polynomial length. And because we can recognize, once we see a valid solution to the problem, valid witness, we can just, there is a strategy that will work for every binary relation that is efficiently computable. We just try all of them, okay? So if you look back to many of the problems that we have been solving through this class, the sort of algorithms that we'll be designing are alternatives to the brute force search. Like in many of the problems that we study in this class, you could always say, well, you know what? I don't really know what to do. I don't know what to do in terms of an intelligent solution to the problem. I always have the option of enumerating all possibilities. This is to say that, yeah, enumerating all possibilities is a possibility. And we typically try to avoid that, and we want to come up with a poly X algorithm, okay? So we want to understand the question of, can the side R be solved efficiently, which means in poly X time, okay? And now, from this perspective, we see that solving the problem in poly X time basically is a smarter alternative to brute force search that teaches you something about the problem, because you're solving the problem without looking at all the solutions. All right? And at the beginning of the course, we kind of emphasized kind of why are polynomial time solutions better than exponential ones. Philosophically, one of them is that, well, you're not iterating through all solutions, so you must have learned some structure about the problem by sort of not touching all solutions and still all candidate solutions and still solving the problem. Yeah, so the summary is that we have a generic the side R can always be solved in exponential time, and really the question is, for what relations can R be solved in poly X time? Okay, so this leads to the notion of P and NP, okay, that I'm going to define right now, okay. You want to make space for that, so I'm going to cancel this question. So now we arrive to the definitions of P and NP. So we're going to say that P is a complexity class. What is a complexity class? It is a set of computational problems. Now for us, in this lecture, a computational problem is a relation. So we're going to say that P consists of all relations R such that the side R can be solved efficiently. Okay, so there is a polynomial time algorithm that is able to solve the decision problem. And because there is a polynomial time algorithm, it is a better alternative to brute force search. NP is going to be all computational problems, so R. And that's it, or at least up to the technical condition that is important to include, that R is efficiently computable. Now clearly, if R can be solved efficiently, then R is efficiently computable. So that's why kind of all P relations are contained in NP relations. And the question of are these two sets the same is tantamount to asking, is it the case that every efficiently computable relation is such that its corresponding decision problem can be solved efficiently? Okay? So you probably already know that the answer to the question is open, right? And one way to understand it is that is there a way to mechanically avoid brute force search, right? Because again, we can always do brute force search for any NP problem to solve our problem. But what we're asking is there a polynomial time solution? Like, is it always possible to avoid brute force search? Okay? Now, and so far in this course, we have been basically kind of studying specific problems inside here, and sometimes we have been relating these problems to reductions. But at the end of the day, we always had an algorithm, right? If we want to try to understand this space, one option, of course, is to say, well, let's take something that is here, and let's try to move it in here by giving it an efficient algorithm. But for all we know, these two classes could be different. So there could be all kinds of problems where we cannot put them in P because maybe no efficient algorithm exists to solve the decision problem. Yet we have to somehow try to understand the kind of this landscape of why are some problems hard, or how are some problems hard? Why are they not in P? And reductions is going to be the way that we do that. So this lets us introduce. We're going to introduce some notions, okay? So an important definition is that of NP hardness. So we're going to say a problem A, a relation A, is NP hard if for every B in an NP, so for every other relation in NP, B can be reduced to A. Namely, if you have an algorithm to solve the decision problem associated to A, you can use that algorithm, you can kind of use a reduction to turn that algorithm into an algorithm that decides the decision problem for B for any B in NP. Okay? So this A every problem in NP can be reduced to it. So to some extent, A is no easier than any other problem in P, or at least the hardest problem, or among the hardest problems. Okay? Now, I wrote A's in NP, but we actually don't know that, right? Because NP problems are not all computational problems. There are problems that are much harder than NP. For example, the halting problem. So if I want to say that A is not only as hard as all of NP, I want to specifically say that A is an NP, then that is a separate definition. We say that A is NP complete if A is an NP and it is NP hard. Okay? So in this case, this picture would now be correct. All right, so basically our attack plan is to say, okay, look, if we want to try to understand NP, then one way would be to say, well, we can try to identify which problems seem hardest within the class. And if we do that, then when you come up with another problem that you're wondering, I wonder if this problem has an efficient algorithm, and you keep looking for an efficient algorithm for it, and you keep failing, maybe you can say, well, maybe it is NP complete. If you're able to prove that it is NP complete via reductions, then you know that probably you should not be looking for an efficient algorithm for it, because if you were to find an efficient algorithm, that would show that P equals NP. Okay? So kind of showing the problem is NP complete is strong evidence that probably this problem does not have an efficient algorithm for its decision problem. Now this plan hinges upon us even having NP complete problems to begin with. And so here comes a pretty kind of fundamental question, which is, do NP complete problems exist? And the answer, which in retrospect is kind of obvious, as will be clear in a moment, but is a kind of a deep realization, is that the answer is yes. Okay. So I'll give right now a problem that is NP complete. So we're going to say that the circuit SAT problem is the binary relation R sub CSAT such that R sub CSAT given an instance, well, what is the instance? It's going to be a Boolean circuit. We defined Boolean circuits last time. An input for it. Well, last time we kind of hard-coded the inputs into the Boolean circuit, but we can consider it as a separate object. And an instance X and a witness W is in the relation if C of W equals 1. Okay? So I'm actually going to write it in a different way. So C and W is in R CSAT if and only if C of W says 1. So if you have a Boolean circuit, you evaluate it on input W equals 1. Okay? So, and now we have a simple claim that CSAT is NP complete. Okay? And the proof is kind of pretty straightforward. Well, to prove that it is NP complete, we need to show, first and foremost, that it is NP. Well, CSAT is in NP because this process is efficiently computable. Okay, so let's unpack this. Remember that a problem is in NP if the decision problem is efficiently computable. Well, here I need to decide whether, given an instance X, which is the circuit, and a candidate assignment W, if I evaluate the circuit on the input, do I get 1? Is that something I can do efficiently? Sure. Again, you take the circuit, you topologically sort it, and you just evaluate it on the input, kind of gate by gate. So it is certainly a problem in NP. But CSAT is also NP hard because everything in NP can be reduced to it. And how can we see that? Well, pick some problem B in NP. Okay? Because it's an NP, the relation of B will have a verifier, right? So because B is an NP, it has an efficient verifier B, right? That kind of takes instances of B and witnesses of B and kind of does the right thing. Okay, it kind of decides according to the relation of B. So there is an efficient verifier. But this immediately gives us a reduction, right? Because say that now I want to come up, I want to solve the problem B with a subroutine that is CSAT. How would I do that? Well, I get my instance of B, and I need to decide whether there is a witness for this instance of B. In my preprocess algorithm, I'm going to let me make a little bit more space here. In my preprocess algorithm for the reduction, I'm going to output the circuit for the computation V sub B, XB, and I leave this input unbound, right? So again, there is an efficient algorithm for deciding B. Take that algorithm and give it a witness, right? Take that algorithm, hard code in it the input XB, and I'll take that computation and unroll it into a circuit, right? We already discussed last time that unrolling into a circuit is not something we can talk about formally in this course because we don't have definitions for Turing machines, but it is something that makes sense, right? Because you have an efficient algorithm, unrolling it will give you a polynomial size circuit. So do that in the preprocessing. That will give you some circuit. Now you pass this to the algorithm for CSAT that we are kind of presuming exists. It probably doesn't, but in a reduction, we're saying presume an algorithm for CSAT exists. It will give you back a W that makes that circuit accept. But that is tantamount to being a solution to the original problem. That is also a witness for the problem B. So if I look at this entire chain, this is an algorithm for the problem B, because we have kind of programmed our CSAT algorithm to provide it an instance C whose witness is a witness for original problem. Okay? So this shows that kind of CSAT is NP complete. All right. So we have found one NP complete problem. And in order to develop our sort of theory of, or at least to make the theory of NP completeness usable, we need to kind of be able to reduce other problems that look hard to us to NP complete problems, or at least, sorry, to reduce NP complete problems to our problems of interest, okay, to show that they're hard. So what we're going to do now is we're going to show that another problem is NP complete, but this other problem is going to have a simpler structure than CSAT, okay? And over the course of the rest of this lecture and the start of next lecture, we're going to come up with the simplest problem that we can that is NP complete, and using that simple problem, we can then go out and show that a number of other problems that a priori you wouldn't guess are NP complete are in fact NP complete, okay? Remember, like CSAT is kind of, in retrospect, almost obviously NP complete, right? Because CSAT is generic computation, and here you're just saying, well, is there a witness that makes a generic circuit output 1? Well, that is precisely kind of what NP hard means, okay? All right, so our first simplification will be to show that not Boolean circuits, but Boolean formulae are the satisfiability problem when Boolean formula is NP complete. Okay, so that's the first simplification we're going to do on CSAT, and I'm going to do it here. All right, so first I need to say a little bit about formulas versus circuits. So we already discussed circuits, Boolean circuits. They are just directed acyclic graphs of gates. So you have some inputs, and you have gates internally, and it's just kind of computing in some a reasonable way, right? So you have, and at some point you produce some outputs. Okay, so it's a direct cyclic graph of gates. A formula is a tree. Okay, so another way to view it is that you are not allowed to reuse subcomputations. Okay, so it's a tree of gates. Like for example here, notice that this gate, the output of this gate is reused as an input to this gate and also as an output here. But here, no output of any gate is reused. Okay, so that's called, this is a formula, that's a circuit. Boolean formula, Boolean circuit. And by the way, what are these gates? You know, these are the ANDs. It could be an OR here, right? And maybe down here you have also an AND. So Boolean logic. So just like you can define the satisfiability problem for a Boolean circuit, we can define the satisfiability problem for a Boolean formula. That problem has a name, it's called SAT. Okay, so SAT is the following problem. Given a Boolean formula, phi, let's say from n bits to 1 bit, they always have one output. Decide if there exists a witness W, has n bits, such that that makes the formula satisfiable. Okay, so that is the decision problem SAT. Again, to be distinguished from CSAT, where C denotes the circuit SAT. We're going to prove that SAT is NP complete. Okay? So remember, when you want to prove that something is NP complete, you have two things to prove. The first thing you want to prove is that SAT is an NP. How do you prove that SAT is an NP? Well, you need to prove that the corresponding relation is efficiently computable. So, namely, given X and W, is there an algorithm to decide if the formula evaluates? So, given an instance phi in a witness W, is an algorithm to decide if the formula on the input W equals 1? Well, yes. I mean, just evaluate the formula. It's even a linear time algorithm. Right? So if you go back to this tree here, if I assign specific inputs here, 1, 0, 0, 0, 1, 0, and I ask you, for this input, does this formula output 1? You can just go layer by layer and just compute. So that is a linear time algorithm. Clearly, SAT is an NP. Okay? So that's one part. The other thing is to prove that SAT is NP hard. In other words, for every problem B in NP, it is the case that B can be reduced to SAT. Namely, you can use an algorithm, a decision problem for SAT to solve the decision problem for B for any problem B in NP. Okay, but here's where we want to start using NP completeness. We already have one NP complete problem. So rather than showing that kind of, again, starting from any problem in NP and say, kind of directly showing that everything in NP reduces to SAT, it suffices to show that CSAT reduces to SAT. Why? Because here's the picture. We already proved that CSAT everything in NP reduces to CSAT, and if we just prove that CSAT reduces to SAT, then transitively, everything in NP will reduce to SAT, okay? So we can just focus on proving this reduction over here, because we already have an NP-complete problem, right? So once again, because you already have NP-complete problems, if you want to prove that some other problem is NP-complete, it suffices to show that it's NP, and that it can be used to solve some NP-complete problem. This way, okay? So now we want to show how, given a decision problem for SAT, we can actually solve the CSAT problem, okay? So this we're going to do a little bit carefully. All right, so let's maybe kind of at least understand what is the difficulty, because so we're trying to go. So what is it that we want to do? We want to have, remember, reduction has a pre-process, right? And a post-process. And in this case, we're reducing CSAT to SAT. It means that we'll get the pre-process algorithm gets as input a Boolean circuit C. It has to spit out a Boolean formula phi. We pass this as an input to an algorithm for SAT. Again, it doesn't exist, but we're kind of thinking it exists. It will spit out a solution, I don't know, A, okay, for the algorithm for SAT, or rather it will decide. It will say yes or no, okay? And then, here we forward that solution, or at least, yeah. Kind of post-process today is not very important. So, and this entire thing, we want to be an algorithm for CSAT. So, how do we turn a circuit into a formula? Now, a naive way to do it would be to just say, open up the DAG into a tree by copy-pasting subparts of the tree, so of the DAG. Okay, so let's look at maybe attempt number 1. Let's call it. Say that your DAG for the circuit looks like this. Okay. So it's definitely not a formula. One attempt would be to say, okay, let's try to take this and just directly turn it into a tree. So I'm going to duplicate into something like this. Okay, so I can do this transformation. But this is not quite sustainable, right? Suppose that my DAG looked like this. Now, when I open this up, actually now I'm going to have a pretty large formula, right? So it's going to look like something like this. So if you kind of continue this example, actually this transformation of just opening up kind of in a naive way the DAG into a formula is actually an exponential blow-up. And we cannot afford that, right? Because remember that the pre-processing algorithm has to be efficient. So we're going to be doing something else instead. We cannot just literally open up this into a formula. I'm going to erase this because this was just an attempt. So the idea is we're going to introduce auxiliary variables so that actually the formula is going to have polynomially many more variables than the circuit does. I mean, the circuit has some number of inputs, but what we want to do is we want to explicitly talk about its wires. So I'm going to use an example, okay? So let's say our circuit looks like this. So has 4 input variables. And the circuit has an AND here, an OR here, an AND here. Here we reuse this output. So that's why it's not a formula. We pass it into a NOT gate, and we take these 2 outputs and pass them through an AND gate again. Okay, so this is a circuit. So we're going to introduce auxiliary variables that will play a role in the formula. And these auxiliary variables are for all the intermediate wires. So I'm going to call this wire variable x5. Okay, we just finished x4, so I'll start x5. This one is going to be x6. By the way, this is the same wire, so still x6. And here we have x7, x8, and x9. So I introduce one new variable per kind of internal wire of the circuit. And now we can write an equation for each gate. Kind of what the gate is supposed to, like for the circuit to be satisfiable, we can just say that, well, the circuit computes correctly and x9 equals 1, right? So we can say x5 is what? Well, it is the AND of x1 and x2, right? x6 here is the OR of x3 and x4. x7 is the AND of x5 and x6. x8 is the NOT of x6. And x9 is the AND of x7 and x8. Okay? So how many such equations do we write? We write 1 per gate. So this is not many equations to write. And then what we can do is we're going to do a dictionary. We're going to translate each of these equations into a sub-formula. Okay? Let's call it phi1, phi2. I'm going to explain that how we do it in a moment. Phi4, phi5. So we're going to kind of construct a teeny tiny formula for this equation, a teeny tiny formula for this equation, and so on and so forth. We have 5 equations, so here are 5 sub-formulas. And the final phi is going to be the end of all of these formulas, okay? Now, if you have a bunch of formulas and you end them, certainly you have, again, a formula, because that's like attaching another layer of the tree. So I only really need to explain how you're going to convert this equation into a formula. Now, in this equation, we have pieces that look like formulas. Like this part looks like a formula, that part looks like a formula, this one also, this also. The only thing that inside this equation that doesn't look like a formula is the equality sign. This is the part that needs to be translated. Like formulas don't have equal signs in them. You can have ands, ors, and nots, okay? So this equal sign kind of doesn't belong. So the idea to do that is that we have some small gadget that is going to implement the equal sign using and, ors, and nots, okay? So let me do it up here, okay? We're going to say equal sign in formulas, okay? So suppose I have some generic formula phi1, and I want to say that formula should equal phi2. I can also write this in a different way and say, look, this formula will evaluate either to 0 or to 1, and this one will also be 0 or to 1. So this is the same as saying either both of them are 1, or both of them are 0. Okay? So this is my gadget translation. Whenever I see an equal sign with a formula on the left and a formula on the right, I rewrite it as this expression over here, which is also formula, and it's only twice larger, right? here we were applying it to small gadgets. So this entire thing is now a formula where the size of phi was the size of the circuit. So this entire translation into formula created a formula that is not much larger than the circuit. Okay? Whereas before, when we were just opening up things, you were creating a formula that was exponential size. Now, this new formula, we need to make sure that when we decide its decision problem, it tells us about the decision problem for the circuit. But the formula we constructed is the computation of the circuit, right? So if there is a way to satisfy the new formula, then there is a way to satisfy the original circuit, right? Because all the auxiliary variables are kind of bound to respect the computation of the circuit. Conversely, if there was a way to satisfy the circuit, then there is a way to satisfy the formula, namely just compute the values and put them in, it will be satisfiable. Okay, so this proves that the decision problem SAT is also NP-complete. Now, why are we doing that? Because we want to simplify that and well, first we want more NP-complete problems to work with, because when you have some other problem that you're trying to show it's NP-complete, it is easier if on the shelf you have more NP-complete problems to start from to prove things like this. But also we want the NP-complete problems to be simple, okay? So clearly, trees are a special case of DAGs, right? So formulas are a special case of circuits. If you can show that the satisfiability problem for a simpler type of object is NP-complete, that is like a stronger result, right? So here we've made one first step, and we said, yeah, actually, you don't really have to think about CSAT, it is NP-complete. It suffices to think of SAT for formulas, a much simpler object. Starting from here, next time we'll show an even simpler type of formula, so-called 3SAT, is NP-complete, okay? And once we have that, we'll be able to show that certain other NP-complete problems that seem to have nothing to do with Boolean logic, for example, problems about graphs, are also NP-complete. And the fact that we were starting from 3SAT is very helpful. Okay, so that's the plan for next time, where we're gonna start off and talk about 3SAT.